Okay, so we're going to look at solving rational equations. Solve rational equations and verify their solutions, right, is what the goal is. So here is salt water is flowing into a large tank that contains pure water. The concentration of salt in the tank, C in grams per liter at time t in minutes, is given by the formula. C is equal to 10t over 25 plus t. We're supposed to determine the time when the salt concentration in the tank reaches 3.75. Okay. So we want 3.75 is equal to 10t over 25. So basically, we're going to solve an equation, right? So the steps in solving an equation would be to factor the denominator, right? We're always doing that, but it already is in factored form, right? There's nothing to factor. Be to state the non-permissible values. So what can't t be? Negative 25. Now, since t is time, it's not going to happen that it is negative 25, right? But something we have to keep in mind with solving a rational equation is if there's a context to it, and this one has a context, right? What's the amount of time? If there's a context, then we know, well, time has to be greater than 0, right? Greater than or equal to 0, maybe, but it can't be negative. So if we solve these, and we get more than one solution, which is possible, if you have a quadratic so that it solves, you get two values, then we have to start saying, okay, what's the context for this problem? Is this solution allowable, or does it need to be rejected, right? We say, okay, we've got a negative time, we need to reject that. Now, in order to solve this, we basically need to get rid of the denominator. So to do that, we're going to multiply both sides by the denominator. So we get 3.75. Let's put it over 1, just so it kind of looks like a fraction. And multiply that by 25 plus t is equal to, we've got 10t over 25 plus t, and we're going to multiply that by 25 plus t. Not 25 plus t over 25 plus t. We're not looking for an equivalent rational expression. We're looking to multiply by the lowest common denominator so that these guys cancel. So what we want in the end is I want 1, 1, 1, 1. I want all of the denominators to be 1. So now we'll just have a linear equation, right? Just an equation with numbers and t in it, and we can solve for t. So we now multiply 3.75 times 25. I'll let one of you guys do. It's like 100, it's 75, and then 80 something, point something. 93.75? Sorry?
Yes.
Yes. Okay, so that's this times this, plus 3.75t is equal to 10t. Okay, so the idea is factor the denominators, right? Figure out the lowest common denominator. It's kind of like add or subtract to that point. Multiply through by the lowest common denominator so that all the denominators end up as 1s, and then solve the resulting equation. So to solve this, we're going to keep the 93.75, and we're going to subtract, move this over, it'll be subtract 3.75t. So 93.75 will equal 10 minus, so what's that going to be? You need a quarter to 6 1/4. So 6.25t, and then divide both sides by 6.25, and end up with t is equal to 15. And then it's 15, whatever the time units were. So what does the problem say the time units were? I think it's probably minutes or something, right? Time in minutes. So t equals 15 minutes. Okay, so that's the steps, right? So whatever you do in rationals will always involve factoring the denominator, right? Whether you're doing simplifying, whether you're doing multiply dividing, whether you're doing adding or subtracting, you need to factor the denominator, state the restrictions, okay? And the restriction was it can't be negative 25, and that's fine because it's not negative 25, right? It's 15. If you want to check your answer, you can go back here and go 10 times 15, which is 150, divided by 25 plus 15, which is 40. 150 divided by 40 should give you 3.75, right? If it does, you know you got the right answer. And it does. Verification comes from the back there. Okay, next. All right, and then they're showing a solution here. Same deal, explaining what's going on here, showing, multiplying by this. You know, I like to put little ones down everywhere so we can see the ones. I solve for t. So rational equation, an equation that involves one or more rational expressions. And the equation part just means you're going to see an equal sign in there, right? That's what makes it an equation. Everything else is just rational expressions, right? What can you do with a rational expression? You can simplify it. You can come up with equivalent rational expressions. You can multiply rational expressions. You can divide rational expressions. You can add them. You can subtract them. The only thing you can solve is an equation. Everything else just gives you another rational expression, right? Usually a single rational expression, which is generally simpler unless we're going for equivalent. And then it might not be simpler. Okay, next one. Solve a rational equation with an extraneous root. Okay, so we got 18 over x squared minus 3x is equal to 6 over x minus 3, short-term memory, very poor, minus 5 over x. Step 1, always factor the denominator, right? So we do have a denominator factor. Okay, so 18, now it's just a common factor, right? Check it out, x squared minus 3x, good, you know, I factored it correctly. Okay, at this point, what are my restrictions? Okay, so 0 and 3. Now, there's no context to this problem, right? In the sense of, it's not an amount of time we're solving for, so we don't have the context of, well, hey, time has to be greater than 0, right? Or we're solving for the length of a rectangle or something. We say, well, it's got to be positive, or you can't have a negative length. So we're not worried about that. The next step is to get rid of the denominators, right? So where I see this, this, and this, I want to get to the point where they're all ones. So what's my LCD? Yeah, so we need an x minus 3, right? It's just what the denominator of that first term is. So I'm going to multiply every single term by this, by x times x minus 3. I'm going to throw that in brackets. So that's the first term, the term on the left. Now how many terms are there here? There's 3 of them, right? So we have to multiply these 3 terms. So then x times x minus 3. I like to put it over 1, right? Just so that I know that it's, you know, got a numerator and a denominator. Minus, and again, times 5 over x. LCD is closing in. Let's move it up. Okay. So all 3 terms are being multiplied by the lowest common denominator, right? And now we can do some canceling. So this x takes out this x. leaving a 1, right? Remember, what do I want? Everything down here should be a 1. X minus 3 takes out x minus 3. Got a 1. X times x minus 3, the x's take each other out. The x minus 3's, 1, 1, 1, 1, 1, 1, 1. Okay. So there's no denominator, right? That's what the idea here is, get rid of the denominators. Always keeping in mind the restriction, right? Okay, so get rid of the denominators. So now let's go through and simplify. I've got 1 times 1 times 18. 18 equals, I have x, kind of almost looks canceled. But okay, I have x times 6, which is 6x, minus, and I have 5 times x minus 3. I'm going to just throw a bracket down there. Right, because I have to subtract whatever this multiplies out to, right? So I just want to remember subtract, but after I've done this. So 18 is 6x minus, and in here we get 5x minus 15. So we go with round brackets there. So 18 is 6x minus 5x plus 15. So we're distributing this negative through the brackets, right? It's going to be minus 5x and then plus 15. These signs are going to change. That was positive, it's going to be minus, that's negative, becomes positive. Okay, so we got 18 is equal to x plus 15, subtract 15 from both sides, end up with x is equal to 3. What's the problem with x being 3? It can't be 3, right? Why can't it be 3? So, well, that's what we said up here. Once we had the factored form, right? Can't be 3, can't be 0, can't be 3. If I try and put a 3 in here, I end up with 6 divided by 0. It's undefined. All right, so what happened? When we solved, we went through, we multiplied out the lowest common denominator. We got a new equation, which can be solved. The problem is, when that new equation was solved, we ended up with an answer that won't work. Okay? Where does it work? It works here. It works in this, but it doesn't work in the original. So we cross this off, and we say, no answer. Or the solution set and that's a notation we haven't learned yet, but we will be learning when we do set theory. And that's the empty set. Okay, so when you see a brace bracket, that means the set of, and inside there it's like a 0 with a slash through it. That means empty, the empty set, which says there is no solution. Right? You can't solve this problem. So if you were trying to solve this graphically, what you would basically notice is there's no intersection between this guy and this guy. Right? There's two separate lines. We're trying to see where do they intersect, and they don't. All right, and then somewhere down here it's going to say there is no solution. This is a non-permissible value. It's an extraneous. It's called an extraneous root. Right? It's a root that is only introduced by the solution method. Okay, and then it says down here, it's the solution of the equation is not permissible in the original equation. An inadmissible, that's extraneous. An inadmissible solution is a solution that is permissible in the equation, but is not valid in the context. Okay, and you're not going to have to differentiate between the two. Just in the end, you just have to reject that solution, right? So it's extraneous if it just doesn't solve the problem, right? It's one of the non-permissible values. It's inadmissible if you end up by saying, and the length should be -3 centimeters, right? No, okay, we can't have -3 centimeters. Or the time is -4 minutes. No, okay, that doesn't happen either, right? We're starting our time at 0, so not at -4. Solving a rational equation with an inadmissible solution. So we know this is going to have a solution which isn't going to work. All right, let's see. When they work together, Susan and Lucy can deliver flyers to all the homes in their neighborhood in 42 minutes. when Lucy works alone, she can deliver the flyers in 13 minutes less time than Stuart can when he works alone. When Stuart works alone, how long does he take to deliver the flyers? So the thing we're trying to solve for is how long does it take Stuart to deliver the flyers? So we're saying let y represent the time that Stuart takes to deliver the flyers when he works alone. Now, Lucy can do it in 13 minutes less time. So y minus 13 is the time that Lucy can do it when she works alone. Now we're trying to figure out, all right, so how much do you do each minute? Well, working together, we know that they will do 1/42nd of the neighborhood in 1 minute, right? Because it takes 42 minutes working together. So Stuart working alone, he'll deliver 1 over y. Lucy working alone will deliver 1 over y plus 13, right? That's what fraction they deliver. And together, that adds up to 1 over 42, right? Because working together is going to take them 42 minutes. But they can deliver each minute they deliver 1/42nd of the flyers, right? Let's say there were 42 houses they had to cover. Each minute they could do 1 house, right? If there are 84 houses, then each minute they could deliver 2. And here's something where it says, I compared the rates at which Stuart and Lucy worked. For example, if Stuart took 80 minutes to deliver the flyers, then how much would he deliver each minute? 1/80th, right? So that's kind of reasoning that they're going through here in saying, working alone, it's 1 over y, right? If it takes me an hour, then I would do 1/60th per hour. Okay. Now we're going to solve this. Okay. So let's show you a solution, because what you could be looking at is the context is laid out for you. Here's the equation. They're going to show us the steps, and there won't be any errors in here because they're actually presenting the solution. But on a test, you might get one of these says, which step is the error in, right? And you're just basically saying, all right, what do we have to do? Well, we got to find common denominator, right? Well, first we got to state that y can't be 0 or 13, right? Can't have a 0, 1 over 0. You can't have 13 because that would be undefined here. So you need to state these because those are your restrictions. Your LCD is y and y minus 13 and 42. So we're going to multiply everything by 42y, y minus 13, right? So that's the first term. They're going to multiply the second term by that, and then we're going to multiply the third term. Now, the only difference that I would make, just get rid of those circles, is I would just write these over 1. Okay, then you cross off 42s. Take out the y minus 13s, take out the y. We got a 1, a 1, a 1, a 1, a 1, and a 1. Okay, so that's the idea, right? We get rid of all of those. We now have a 42, so where do they do that down here, right? Like 3 steps later. So when you're solving a problem, when you're looking at the diploma, you're looking at somebody else's solution, right? This is how they taught their class to do it, because all the questions are written by classroom teachers, and so we're just going through saying, well, this is how I would do it, right? And you have to adapt somewhat to that, right? Saying, well, what are they doing here? And they may show more detail. So this is showing a little more detail. I would have just done the crossing off there. We get down to this. You have 42 times y minus 13 times 1. You've got 42y times 1. And you've got y times y minus 13 times 1. Now, this gives a quadratic. It factors. Okay, it's kind of a weird factorization, right, with 91 and 6 as the factors. You could also use the quadratic formula, right, which you learned last year, and will be on your formula sheet. So they solve, and they say y equals 91 or y equals 6. Now, we know that since Lucy does it in y minus 13, 6 minus 13 is negative 7. She can't do it in negative 7 minutes, right? So we can't have 6 as a solution. It's inadmissible, right? It says that Lucy delivers the flyers 7 minutes before she starts delivering the flyers. Be nice, but not going to happen. Okay, so then y is 91, and what's y? Because by now we've forgotten, right? Oh, y is the time it takes Stuart working alone. What did they want us to find? When Stuart works alone, how long does it take to deliver? So they wanted us to find that. And we have. Okay, so working alone, he does it in 91 minutes. Use a rational equation model to solve a problem. Okay, so let's look at the problem. We'll develop our own solution. So Rima bought a case of concert t-shirts for $450. Okay, so if she bought 45 shirts, how much did she pay for each shirt? $10. Yeah. Okay, it's good to keep an idea of that. She kept 2 shirts for herself and sold the rest for $560, making a profit of $10 on each t-shirt. How many t-shirts were in the case? Okay, so case was 450. She kept 2 shirts, sold them for 560. Whoops. Okay, so case of t-shirts was $450. She kept 2 shirts, sold the rest for $560, made a profit of $10 on each shirt. So the question, I think, was how many shirts were there, right? Like how many shirts in the case. So that's going to be our variable, right? What do we want to find? So let X be the number of shirts. Now what's profit? It's the difference between what? How much you sold the shirt for minus how much it cost. Wow. You're supposed to say this so I can eat. No. It's beef. Look, it's like a melted puddle. So if you buy the shirt, so she made a $10 profit on each shirt. So if she bought the shirts for $12, then she would have sold them for $22 each, right? So we need to figure out, if there were X shirts, how much did each shirt cost? So if there were 10 shirts, how much would each shirt cost? Case of t-shirts, spent $450. If there were 10 shirts in the case, then each shirt would have cost $45, which is ridiculously expensive. It's not that, but the idea is just to give us an idea of what are we going to say with 450 and X. So if it's 450 and X were 10, how did you get 45 bucks? You divided, right? So the cost per shirt, what we want is the cost, actually we want the cost per shirt over here, so cost per shirt. We've got the selling price per shirt, selling price per shirt. And what's the difference between them? So she sold each shirt for this much money, each shirt cost this much money, and how much did she make on each shirt? $10. That's going to be $10. So we figured out the cost per shirt was 450 divided by X. Right? There were X shirts in the case. If there were 10 shirts in the case, it would be $45 a piece. If there were 45 shirts in the case, that would be $10 a piece, right? And you can figure that out. You don't need much in the way of math to do that. You just got to think of buying a case of stuff, right? And we've all bought, cases or, multiple of some item at the supermarket or something. How much is each one? Selling price per shirt. Well, she sold them for $560, but how many shirts did she sell? How many did she keep? 2. How many were there originally? X. How many are left? X minus 2, right? That's how many shirts she... So if there were 30 shirts to begin with, she's selling... Sorry, don't use 30. She's selling X minus 2, right? She kept 2 for herself. The difference between that... This is a larger amount of money, right? It's $560. And that's equal to 10. Okay, what's your non-permissible values? Or your restrictions? What can't x be? 0 or 2, right? Okay, well, we know that likely not $225 a piece for the shirts, and besides, if she kept 2 shirts, then there's none left to sell, right? So you're not going to have to worry about those numbers popping up in the solution, right? Okay, what's my LCD? X and x minus 2, right? So we're going to go through, we're going to multiply each term by x times x minus 2. So here's the first one, 560 over x minus 2. Okay, wait, I just need a bracket there. Minus, okay, same deal, x times x minus 2 over 1 times 450 over x is equal to x times x minus 2 over 1 times 10 over 1. Okay, so anytime you want to make something into a fraction and it isn't, like it's 10, then write it as 10 over 1. Okay, I got a 1, I got a 1, good. Got to get rid of that x, which takes out that x. Get rid of the x minus 2, which takes out this x minus 2. So I'm left with x times 560, right, which is 560x, minus 450 times x minus 2 is equal to 10 times x minus 2, right? So we're just going to rewrite these putting the number first, right? 10 times x minus 2. Okay. Now we need to expand this. So 560x. Okay, watch your signs here. So it's going to be minus 450x plus 900 equals, so treat this as one number, so it's 10x squared minus 20x. Okay, so we have a quadratic, right? So we're going to take all of this and move it over, but before we do that, we'll do just a little more simplifying. So I'll just extend the page a bit. So we got 560 minus 450 is 110x. Plus 900 is equal to 10x squared minus 20x. Okay, that's just simplifying that line. Okay, move everything over, move this stuff. So we'll get 10x squared. Subtract 110 gives me minus 130x. Subtract 900 minus 900. And that's going to be equal to 0, right? Because we've cleared this side, right? We subtracted 110, we subtracted 900. This side is now 0. We're just going to reverse the order we write the sides. Since it's an equation and it's equal to 0, we can divide through by 10. Right? And all of these guys are divisible by 10. So I get x squared minus 13x minus 90 is equal to 0. We know that x has to be a whole number, right? Because you do not buy a case of 3.7 shirts. Right? There's 3 shirts, or there's 4 shirts, or there's 5, whatever. So I need 2 numbers that multiply to 90 and differ by 13. 18 and 5, right? No. X minus 18, x plus 5. Okay, so you get x squared plus 5x minus 18x is minus 13x minus 90. Which means that x is equal to 18, or x is equal to negative 5. Now you can't have negative 5 shirts. So that's an inadmissible answer, right? It's not allowed. You can't have negative 5. So there must be 18 shirts. Okay, so there were 18 shirts. Now it's reasonable to go back and check. So let's go back to the original problem. Bought a case of t-shirts for $450. So what's 450 divided by 18? Right. There are 18 shirts. 25? Exactly. She sold 16 shirts for $560, right? So she kept 2 for herself. So what's 560 divided by 16? So she sold them for 35, she bought them for 25. How much money did she make off each one? Okay. So that matches, right? So you can go back and you can check your answer, right? By saying, all right, if you bought 18 shirts for $450, you spent $25 on each shirt. If you kept 2 of them, then you sold 16 of them, you got $560, you got $35 for each shirt, you made a $10 profit on each shirt. Okay, life is good, it all fits. I solved for x by factoring, and then since negative 5 is an inadmissible solution, it doesn't make any sense. And there's 18 shirts in the case. Key ideas. You can solve a rational equation algebraically by multiplying each term by the lowest common denominator. So your steps: factor the denominator, state the restrictions, right? That's a step in everything. No matter what we're doing, right? Always factor the denominator. If you're going to add or subtract, you're only factoring the denominator. You want to factor the numerator when you're simplifying, right? Because then we're looking to say, can we cancel anything? You want to factor the numerator when you're multiplying or dividing. Okay, so factor the denominator, state the non-permissible values, multiply each term by the lowest common denominator to eliminate fractions, right? Nobody likes fractions. So we multiply by the LCD, we get rid of the fractions. If a root of the rational equation is a non-permissible value in the original, it's extraneous and must be dismissed. So I wrote a question on the weekend where it would solve nicely, and one of the solutions was a non-permissible value, and the question was just basically asking the solution set is, and it was going to give you these numbers. So if you solve it and ignore the fact that it's a restriction or non-permissible value, you're going to pick the wrong answer. Right? You're going to find an answer that matches nicely with, the stuff, but it's not the right answer. Need to know, each solution can be verified by substituting into the original equation. If it's a word problem, go back to the words and just see if the situation makes sense with the numbers you have. Forget about equations. Just think about the situation and take the numbers you have and put that into the situation and try and figure stuff out. Forget about equations and just see if it makes sense. If the left side equals the right side, it's a valid solution. When solving a contextual problem, it's important to check for solutions that are valid. So negative 5 was a perfectly valid solution to that equation. But in the context of shirts, it is not valid to have negative 5 shirts. Okay, so that's inadmissible in the context. And again, you may get a problem like that as well, right? On the exam where the solution set is all nicely laid out, and they ask you the solution is, or the solutions are, and here's all these answers, and one of them has a solution that's not right in the context of the problem and has to be rejected. Okay. And that's what they'd be testing, right? It's not really your ability to solve. They're going to solve it for you, or mostly solve it for you, get it down to maybe here's a little quadratic that you have to factor and solve, but it's fairly easy to solve, and then ask you, okay, now, what about the answer, right? All right. That's it for this.